Hello, I'm Jonathan Gilligan. Today I'll be talking about incorporating behavior into socio-environmental systems modeling. I'll begin by talking about why behavior is important. I'll talk about challenges of incorporating behavior into models and then draw on case studies to show you how some people are addressing these challenges. I'll focus a little bit on the problem and challenge of making quantitative predictions from behavioral models of socio-environmental systems, and then wrap it up with conclusions and steps forward. Human behavior is at the core of coupled socio-environmental systems and their dynamics, but most models of socio-environmental systems represent behavior simplistically, and this lack of sophistication limits the model's value for understanding the dynamics of these systems and for addressing socio-environmental problems facing society. A recent paper pointed to this deficiency with its title, "The Earth Has Humans, So Why Don't Our Climate Models?" and called for prioritizing better representation of human behavior and the dynamics of interactions between behavior and climate change. An important impact of climate change is its effect on human migration, but the connection between environmental change and migration is complicated, and modeling it requires better representing behavior. The historian Sunil Amrit cautions against simplistic deterministic interpretations of the connections between environmental change and human migration. He writes, "Migrants did not react blindly to the furies of nature. Each act of migration arose from the hopes of individuals or the grim calculation of family survival." Biswajit Malik has called attention to the need to better represent the psychology of migration through his work on environmental non-migration, studying the factors that lead people to take psychologically complex decisions not to migrate in the face of environmental stress or disaster. This photo shows people in Bangladesh who move to an elevated road to escape floods in their villages. They exhibit complex behaviors and social interactions in their migration, with communities of migrants that regularly come together each time they migrate. A review by Tober, Schwartz, and Hermans of agent-based models of environmental change and migration found that most models disregard that migration emerges from the complex decision-making of heterogeneous individuals and their interactions, and that even among agent-based models, which are particularly suited to representing decision-making, only 2 of the 14 agent-based models they identified of environmentally influenced migration contained psychological theories of decision-making. Far more often, models represent human behavior in simple economic terms where people rationally or quasi-rationally take the decision that optimizes their expected utility. Understanding human impacts on the environment and transitions to sustainability also depends on behavior. My colleagues and I have shown that attention to individual and collective behavior can be a powerful tool for rapidly reducing greenhouse gas emissions. In the US, household energy consumption is responsible for around 40% of greenhouse gas emissions, more than any other economic sector, and appropriate behavioral interventions have a realistic potential to reduce those emissions by 20% through voluntary actions. In this figure, the light blue bars represent the emissions reduction if everyone took every possible action. The dark blue bars represent psychologically informed estimates of how many people would voluntarily adopt each action if presented with appropriate incentives. We have developed a framework for analyzing sustainability policies that takes individual and collective behavior into account, but few models have incorporated it. Too many models of socio-environmental systems assume that human behavior is little more than the kind of rational utility maximization widely seen in economic models. However, real behavior is often driven by far more complex motives. Policy analysts assume that if clean or energy-efficient technology is cheaper or easier to acquire and use than dirty or inefficient technology, it will be widely adopted. But empirical studies find many counterexamples. When an energy-efficient light bulb will save $10 per year, politically conservative shoppers prefer them if they don't know about the environmental benefits, but reject them if they learn about the environmental benefits. Marco Jansen has shown that incorporating behavior into models poses challenges because there are many theories of behavior, and different theories can lead to different dynamics of the system. He used a simple, stylized agent-based model of a coupled socio-environmental system based on Lovelock's daisy world, in which people's behavior, harvesting white or black daisies, affects the climate under 5 different theories of decision-making. Experiments with this model showed that policies for stabilizing the planet's climate played out very differently under the different behavioral theories, so the success of policymaking, even in a very simple socio-environmental system, depends on the details of human behavior and decision-making. Even within a single model of behavior, there are great challenges in implementation. Mulder and Filatova used an agent-based model of residential adoption of solar power using the psychological theory of planned behavior. The model compared 3 subtly different implementations of this decision theory, each one taken from a different published model. The 3 different implementations of the decision theory run within the same agent-based model produced very different predictions of rooftop solar adoption. Sensitivity analysis revealed that the 3 different realizations of the theory had different sensitivity to the different psychological parameters as well. Like many psychological theories, the theory of planned behavior is ambiguous, and there is not a definitive representation. So any model that uses such theories will involve discretionary choices by the authors about how to implement the theory. The dynamics of socio-environmental systems depend on how individual and collective behavior is represented. So there are challenges both in selecting which behavioral theories to use and in the details of translating those theories into algorithms. A particular challenge is representing the interactions between individual and collective behavior. The simplest attempts to incorporate realistic behavior into models begin with behavioral economic theories such as bounded rationality, risk aversion, or prospect theory. These approaches focus on the individual level but incorporate empirically established deviations from rational utility maximization. 2 closely related theories that are widely used to treat interactions between individual and collective behavior are diffusion of innovation theory and theory of planned behavior. In both of these theories, individual decisions whether to take an action are affected by the individual's perception of how many other people are taking that action. Diffusion of innovation theory and theory of planned behavior can be implemented in either system dynamics or agent-based models. But agent-based models have the advantage that the collective behavior emerges spontaneously from the individual agent's behavior and represent interactions between individuals and groups explicitly, whereas in system dynamics models, the individual behavior is not represented, so they only consider the collective behavior. A recent paper by Alexander and Bloch uses diffusion of innovation theory in a model of how farming communities in Ethiopia may use seasonal weather forecasts in deciding what crops to plant. In the model, a seasonal weather forecast becomes available, but farmers don't know how much to trust the forecast. Following diffusion of innovation theory, the farmer agents in the model are divided into 3 groups: early, middle, and late adopters. Early adopters are more comfortable with risk and have a more trusting attitude toward novel technology, so they're the quickest to use the new forecasts in their seasonal planning. Middle and late adopters are more risk-averse and less trusting, so they're more likely to wait to use the forecasts until after they see others in the community successfully using them to get larger harvests. There's extensive empirical work observing this kind of segmentation in many contexts, and Alexander and Bloch draw specifically upon ethnography and surveys to calibrate their model to Ethiopian farmers' attitudes. In this model, farmers' trust in the forecast is represented by forecast trust units, FTUs. Each group begins with a different level of trust and adjusts its trust differently when a forecast is correct or incorrect. Risk-tolerant, risk-neutral, and risk-averse farmers adjust their trust in the forecast differently, depending both on the type of forecast, normal, dry, or wet conditions for the growing season, and on how accurate the forecast is. The model adds additional behavioral complexity by including social interactions in which farmers' initial trust in the forecasts is modified by other farmers' trust or distrust. These social interactions slow down adoption by the earlier adopters, but speed it up dramatically among the later adopters, producing a more uniform rate of adoption and increasing the overall economic benefit to the community, as well as reducing economic inequality. Model experiments found that the benefits of seasonal forecasts for enhancing food and water security depended on the details of individual and collective behaviors and attitudes, such as risk perception, perception of peers' trust in forecasts, and peer-to-peer learning. The model demonstrates that successful policymaking also requires attention to public engagement and the dynamics of social interactions in the community, in addition to developing reliable meteorological forecasts. Now I'll talk about another model by Beckett et al., which uses the theory of planned behavior to add human behavior to an integrated assessment model of energy use, greenhouse gas emissions, and climate change. They start with a system dynamics model, C-ROADS, that simulates greenhouse gas emissions and global temperature change based on scenarios of population growth, economic growth, and the carbon intensity of the economy. They then use a behavioral model to modify the greenhouse gas emissions. Empirical work consistently finds that perceptions of social norms, people's perception of what others expect responsible people to do, have a powerful effect on behavior that affects the environment, such as recycling and conserving energy. Coupled modeling of behavior, energy systems, and the environment allows Beckett et al. To study the implications of this behavioral research for the dynamics of global greenhouse gas emissions and climate change. They use theory of planned behavior to represent the human behavior. In this theory, which can be seen as an extension of innovation diffusion theory, human decisions begin with an attitude toward reducing greenhouse gas emissions. This attitude is shaped by the person's memory of recent extreme heat events, together with the person's belief in whether reducing their greenhouse gas emissions will reduce the future risk of extreme heat. The attitude is modified by perceptions of social norms, and finally, attitudes are further modified by perceived behavioral control. Does a person believe that they can reduce their greenhouse gas emissions? If attitude, perceived social norms, and perceived behavioral control align, the person will reduce their emissions. In the model, this is represented by a series of equations. The person's perceived risk arises from their memory of extreme heat events in recent years, Q of T. In this equation, EV represents the anomalous number of extreme heat events in a year, and lambda W represents the rate of forgetting. The memory of extreme events Q is transformed to a perceived risk P by a linkage function represented by a tilde and a psychological sensitivity parameter A. The perceived risk is transformed into an attitude by means of another linkage function and a perceived efficacy E that represents the belief that taking action can reduce future risks. The perceived social norm is represented by a fixed number n between 0 and 1. This norm is then combined with the attitude A tilde by means of a weight alpha. The behavior taken to reduce greenhouse gas emissions, BC, is then given by the product of the perceived behavioral control, PBC, and the combined attitude and social norm, C tilde. This factor is applied to a function that describes the maximum feasible emissions reduction per year to calculate the annual emissions that is supplied to the C-ROADS model. In contrast to the model of Ethiopian farmers, where behavioral parameters were measured empirically, there are no good empirical estimates of the behavioral parameters for this model. This is a common challenge in behavioral modeling, which I'll discuss later. Beckett et al. Used sensitivity analysis to study how uncertainty about human behavior and psychology affects estimates of greenhouse gas emissions. They found that behavior in the presence of social norms could affect emissions enough to raise or lower temperatures by around 1.4 degrees Celsius relative to the results of a purely economic model of behavior. This means that the psychological determinants of behavior contribute as much uncertainty about future climate change as the scientific uncertainty about the climate system. Beckett et al. Used their coupled model to identify which psychological factors had the greatest impact on the environmental consequences of behavior change, and found that perceived social norm was the most significant factor, followed by the perceived behavioral control, the belief that one could change their own behavior. A more recent coupled modeling approach by many of the same authors has expanded the previous approach to include behavioral phenomena at a greater number of scales by adding the dynamics of political engagement, social networks, and complex feedbacks connecting different behavioral and psychological factors. They represented the complex coupled social, political, behavioral system with this diagram where each circle represents a component of the model, standing for a different aspect of the system, and each arrow represents a mathematical model of the ways in which the components influence one another. One of several factors influencing the opinion circle is the persuasive social force, which is the product of two matrices representing interactions between three different opinion groups. The first matrix represents the social networks connecting the members of the opinion groups. S stands for supporting, N for neutral, and O for opposed to taking sustainability actions. The second matrix represents the persuasive force that people in the network have on others. In these, Fn represents a weak persuasive force by which neutral people influence opinionated ones, and FSO represents a strong normative force by which strongly opinionated people influence neutral ones. A represents the role by which adoption of sustainable behaviors adds to the persuasive force of opinions. There are similarly complex models of the other kinds of interactions and components in this model. Behavior and behavior change also play important roles in models of socio-environmental systems at local scales. McNamara and Keeler developed a coupled model of communities built on barrier islands to study how belief or skepticism about sea level rise due to climate change could shape the politics of coastal protections and thus the evolution of the islands and their communities. They represented the role of belief or skepticism in climate change according to the parameter alpha in this equation, where E represents an agent's estimate of the value of an environmental characteristic such as sea level at a future time t. Alpha characterizes the agent's trust in a climate model. M is the prediction of the model, and S is the historical behavior of the characteristic. McNamara and Keeler used this coupled model to estimate property damage in communities that trusted climate models versus those that did not, and they predict much more damage to communities that do not believe model predictions. This demonstrates the importance of accounting for psychological factors such as trust in models of the economic impacts of climate change. Theories provide a framework, but deriving quantitative predictions from a theory requires calibrating parameters and measuring relevant driving variables. Most of the modeling studies I've presented here cannot empirically constrain their variables and parameters, so they rely on sensitivity analyses to describe what future measurements would need to do to make the models useful for prediction. Unlike hydrological or climatological data, there is very little public data on the psychology of decision-making, and most of what is available has been collected from what are called weird people. Western, educated, living in industrialized, rich, and democratic countries. This limits our ability to apply models in other cultural, political, and economic contexts. Nonetheless, there are promising developments at addressing the lack of data. Knoll et al. Provide useful examples of using meta-analyses of published literature and surveys to obtain such empirical constraints. And de Koning et al. Have developed methods to infer psychological characteristics of human response to flood hazards from empirical data on flood insurance and losses. And they have applied this methodology to an empirical agent-based model of housing markets under threat of floods. Socio-environmental systems modelers have made great progress in the last several years in incorporating psychologically sophisticated theories of behavior into their models. But a great deal of work still remains ahead in terms of improving on those models and gathering reliable psychological and behavioral data to parameterize and constrain them. Taberna et al. Reviewed agent-based models of the interactions between households and institutions, governments, insurance companies, and land developers, in shaping vulnerability and adaptation to flood risks driven by climate change and urbanization. This review shows both that models are becoming increasingly sophisticated and also that there are still gaps in the literature and room to better incorporate behavior into coupled socio-environmental systems modeling.